Good morning, everyone. Thanks for coming to the keynote here at the third iteration of the WITS workshop. Just one quick program note. In the second session, one of the talks, if you refresh the program, one of the talks, unfortunately, we won't be able to have today during the second session about type class specialization. So that's unfortunate, but I just wanted everyone to know about that. It is updated on the website. I'm thrilled to introduce Martin here. Martin Odersky is the lead of the Scala language and professor at EPFL, and is recently getting into looking at effects and capture tracking. So I think we're going to hear more about that right now. Great, thanks.
Thank you. So the title of my talk is Inside the Scala Capture Checker, but I thought that maybe quite a few of you don't really know what is this capture checking and why are we doing this. So I thought I would do sort of a spiral and first come from the outside and say why capture checking, then what is the type theoretic foundation, and then finally essentially how are we actually checking these types or these things. So let me start with that. So why capture checking? Well, it's a cool idea and it's new, but I'm the designer of Scala, so I cared about it also from the Scala perspective. And why is that? Well, because the world has changed quite a bit from when Scala became first popular. When Scala became first popular, it was just one of a handful of the languages that occupied this Goldilocks spot, sort of almost all the way to Haskell, but not quite, and still retaining state, but being mostly functional and being fairly strongly typed, so having very precise types. Whereas the rest of the world was essentially lingering here, either at the bottom, dynamically typed languages, which were sort of functional, such as Lisp and maybe Ruby, or statically typed languages with very small and primitive type systems, which is essentially Java, C#, Go, and all the rest over here. So that was in 2010. But the world has caught up quite a bit. So basically you can say everybody, all the rest moved sort of towards that spot and fairly close to that spot actually, because if we look at what the situation today is that we have a lot of languages that, let me just go back, that essentially acquired lambdas, acquired Java, and recently acquired pattern matching, so they're getting all the functional features. I remember when we talked with the people at Sun in the 90s when we did pizza, they came back and said, well, you do generics, higher order functions, and pattern matching. We have higher order functions because we have inner classes, that's good enough. Pattern matching is not extensible, that's really bad. We just want your generics. And now Java has all of them. So they acquired everything. And a lot of other languages do the same, and there have been lots of new languages on the scene now that are also in this spot. So whether you look at TypeScript or Swift or Kotlin, they're all sort of fairly rich languages with lots of functional features, fairly elaborate type systems, and they are sort of crowding that space. Yeah, thank you. Okay, and then of course there's also Rust, which essentially goes much further in some of the dimensions of strong statics checking in that they also check memory references. So the challenge is so you could say, well, Scala was in a sense successful with the other handful of languages. It dragged the whole industry to where they were. So everybody now has these features, and you can say, yes, imitation is really the highest form of flattery, but for the future, clearly Scala is no longer alone in its space. And I believe it's cleaner, simpler, more expressive than most of the others. But to what degree does that really matter? In industry, it doesn't seem to matter much. There's another challenge that was actually pre-seen by James Eyre a long time ago in 2009 when he wrote this hilarious brief, incomplete, and mostly wrong history of programming languages. So it goes through all the languages. If you haven't seen it yet, then do look it up. It's really very funny. So it ends with this one. It says, a drunken Martin Odersky sees a Reese's peanut butter cup and featuring somebody's peanut butter getting on somebody else's chocolate and has an idea. He creates Scala, a language that unifies constructs from both object-oriented and functional languages. This pisses off both groups and each promptly declared jihad. That was a joke then. It turned out to be actually very true. What happened over the last 10 years in Java, that in Scala, a lot of that happened. There was quite a bit of very bitter fights between people who were in the purely functional programming camp and people who were in the more object-oriented camp, which was denigrated as just a better Java. So the question is, what should Scala become in the future? Should it maybe cede its current space that's thoroughly industrialized and put the emphasis on pure FP instead? And some people think it should do that. They call it a Haskelator jokingly, or monadic Scala, purely functional Scala. But what they really mean by that is that the imperative part of programming, which is always there, should essentially be staged. I don't really like the name pure functional programming. I like to call it staged imperative programming, because it means the effects happen at a later stage in a monad through an effect system. So what people like is, what some people propose is that we should become essentially I don't know, a redder Haskell or something like that. So something close to Haskell. I am not one in this camp, because I believe that if you look at the benefits of functional programming by and large in industry, then there's a diminishing curve. So it's not what promoters claim, that the purer you are, the better. In some domains, definitely, but averaged over the whole industry, I have my doubts. I think there is definitely, it goes very far, but then there's a plateau and maybe even a diminishing returns. We see that in Scala land, where we have lots of very ambitious purely functional projects, and I have the impression that the failure rate in these projects is higher than in the projects that are more pragmatic and have more a mix.
So Haskell on that, down.
I don't know, you have to tell me. So that's also where, in a sense, Scala is, to say we try to hit this plateau where essentially functional plays its strengths and without losing effectiveness. But so in these mostly functional languages, it's not just Scala, it's also OCaml, for instance, or F#, or, as I said, a lot of the industry is moving into that spot. There's a dilemma. So the dilemma is that you have to choose between when to use variables or effects and when to be purely functional. And the problem is, how do you ensure that this happens? You can do code reviews or things like that, but it's very hard. You feel uneasy. A manager wants to have assurances what the code does. And if you have vars lying around and everybody could use them willy-nilly, then bad things could happen in the code base. We've seen that in our own code bases, that there was a single stupid thing that somebody put a var in a place where they shouldn't have put it, and it meant that large parts of the compiler were not parallelizable because there was just a race and we didn't see it, and the var was in such a stupid place that nobody found it. So it was really ridiculous. So how do you ensure this doesn't happen? That's essentially a problem, and that's why many people flock towards purely functional solutions, because then they don't have to decide this problem. So Scala programmers generally really like their guardrails, and that means there's an uneasy choice. You can be simple and performant, no monads, no monad transformers and this thing, but you're unsafe. There's always this bad feeling to say, well, maybe my code is really doing bad things, launch the rockets or something. Or you can be safe and relatively complex and slow. So the problem here is that I think languages should encourage good code. So we use a particular programming language or type system to guide us towards writing better programs. That's the whole point. So ideally, a program that looks simple on the surface should also be safe and predictable. That's sort of what we want. But with effects in these predominantly but not purely functional languages, that's not the case. If you can use an effect, let me just mutate that variable over here. It can make your program shorter, but it would also probably make your program harder to reason about. So the problem is, what looks nice and short on the surface is not necessarily a program that you want to write and that you want to reason about. So The functional answer to that, of course, so far was a staged architecture for effects, where the first stage is a purely functional program that describes a usually monadic computation, and the second stage is you execute the effects in the chosen monads. So it looks a little bit like this. So you have, essentially, this is your program, and then outside is the thing that gets managed by libraries, whether it's a single monad like Zio in Scala, or a stack of monads like Katz effect. So they handle all these things, but they're outside your program. Your program is a first stage, purely functional program that essentially uses these things in a monad. Okay, so that was a solution. It is a solution that is very widely adopted in industry, so much so that people tell me I shouldn't work on effects or capabilities because that's the industrial solution that they will say in Scala. That's the proven thing. The problem with that is that compared to direct style programs that just use the effects, there's a fairly high notational overhead, in particular because monads don't really compose very well. So one typically has to do either higher order acrobatics, such as monad transformers, MTL, finally tagless, and all the Freer monads and all the other inventions, or the other solution is one puts everything in a single monad, which can lead to over-provisioning. And Scala has both. So it has essentially one part of the functional community does that, and is essentially criticized for being very, very complex and very hard to learn. And the other one does that, essentially has a single monad with 3 type parameters for environment, effect, and result. And everybody has to fit into that. 3 type parameters should be good enough for everyone. So the industry experience so far with this, I would say, has been mixed. So people are using that in big projects, but there's also a lot of backlash to say this is too complicated, and there has been quite a lot of sort of walk out to say people walk away from Scala and do Go or Kotlin or other languages just because they don't want to do this kind of stuff. So there has been quite a bad reaction. So the alternative would be to look at it from a different point of view and have a new approach to effects. So what we see here is essentially there's this tension between what our model lambda calculus does, it's pure, it's abstract, and what actual computers do. So computers are full of effects and resources and everything. And languages reflect that. So there are the low-level languages like C or C++, where essentially everything is a mutation and everything is a resource. So essentially I don't have any value that can be arbitrarily used. And then we have higher-level languages like Haskell or Scala and so on. But there's another dimension, and that's to what degree do I track effects and capabilities? And there, I think the answer is, with our current languages, not so much. So the functional languages just say we want to have no effects or as little as possible effects or all effects in a monad, whereas down here the languages typically say, well, effects are just a way of life, we don't track them. Except, of course, Rust has done a big progress here that they have very refined tracking of memory effects. But Rust is, as its heart, even though it has lots of nice functional trappings with traits and type classes and everything, at its heart, it's an imperative language. You have to write a lot. Yes, functional languages need a garbage collector. I think that's an axiom. So the question is, if you go up here to the essentially more lambda calculus-like thing, what happens there? And a lot of research happens there, and some of that has actually found its way into practice, as linear Haskell, the projects like Singularity, Mezzo, there was alias types, algebraic effects are very hot. But the question is, there's nothing really widely deployed, as widely, let's say, as Rust is used in the industry. This is all sort of still very fledgling. And what we have here is another entry in this space, which is called Caprese. Caprese is a acronym for Capabilities for Resources and Effects, and that's a project that we have started last year, and that's going to take 5 years. It's a large SNF project, which we're working on this one. So I'm going to talk a little bit about that. So caprese is about capabilities for resources and effects. The claim is that capabilities provide safe typing for both resources and effects. For us, capabilities are simply implicitly talked values. Capabilities are a very broad term. There are many type systems that sort of have some capability components, but for us, capabilities are really capabilities in the object capability sense. They are values in your program that you pass around. And we have a type system that keeps track of these capabilities, in particular, which capabilities are retained in closures and objects. So for us, the view is more like this. So you still have your mostly purely functional program, but you have all these other things that you can also access, but they're all mitigated by a capability. You need to hold a capability to get to the network or to get to the state or things like that. And these capabilities, they can have limited lifetime and other restrictions, which makes them resources. So ideally, with a system like that, we would arrive at a system where encapsulated effects are very easy to declare, but global effects are hard. The idea is that you should be able to use, let's say, a local loop or something like that, or a local resource. As long as this thing is local, as long as the effect is encapsulated, that's okay. The rest of the program will still see a clean API. On the other hand, a global effect, like a side effect to something that's universally accessible, is really bad. And what we would like to have is a system where that's really hard to type. And with capabilities, indeed, there's a good promise for that, because capabilities would have to thread through the whole program. If you need that, then somebody has to give you the capability, and that's going to be very expensive. So the more local the effects are, the easier a system with capability becomes. So that means we can hopefully soon get to a state where shorter and clearer programs also tend to be safe, and we trust the type checker to guide us to produce good code.
Are capabilities linear? Meaning need to be flipped? Or can they be forked?
That depends on the policy you apply. So in the base system they can be forked, but you could impose a linearity restriction, and we are looking at that right now. Yeah. So the capabilities compared to effect systems, there's some difference. That capability at their core is just a mechanism. There's nothing yet that says they are even used for an effect. They could be used for other things like information flow and things like that. So what our system does is it simply tracks which capabilities are retained. We don't really have any restrictions like with ownership systems where you say there are certain policies where you can't do certain things. With capabilities, is essentially everything is completely free. We just say, well, we have a type system that finds out what capabilities go where, and then afterwards we can add various policies to enforce lifetimes, prevent data races, and so on. And that's essentially the fundamental difference between, let's say, ownership type systems approaches, which start with the policy and say, okay, so here's a policy, your program has to adhere to that, and that's a restriction of your program. Okay, so that was my first part. I want to then switch to second part, which is written in a different system. Apologize for that, for talking about what the approach to capture checking is and what the capture checker actually does. Let me just get, okay. Okay, so we're talking about capabilities for resources and effects, and the challenge that we have is to be actually adoptable in a language like Scala. The notation needs to be really, really simple and intuitive. So there should be next to no overhead for introducing these things. And so what we were mostly looking at is simplicity of notation and not so much extreme expressiveness or essentially we were looking more at what properties we can express simply rather than this full set of properties that we also want to express. So resources and effects are both expressed as capabilities, and the capabilities are tracked in types. So just a quick reminder, what are resources? Resources are values that are available only with certain restrictions, such as lifetime, sharing, quantity. So examples are regions of memories, file handles, channels, database, network connections, and so on. And for us, effects is any aspect of the computation beyond the shapes of inputs and outputs that we want to track in types. So for instance, accessing state, throwing exceptions, doing I/O, suspending a computation, or using a continuation for control operations, and so on. So the problem with effects is that they are transitive, and that makes them a little bit different from other things in type systems. So if you have a calling chain and the final member of Fn has an effect like I/O or assignment or throwing exceptions, then that's indirectly also an effect of F1. Other types don't behave that way. Other types are more local. And the problem is, if that graph, function graph, is dynamic, as it usually is when you have virtual calls or higher functions, then it's hard to describe what the effects of F1 are. So that's the so-called effect polymorphism problem, and it's a problem that has been with effect systems since the beginning 30 years ago. Okay, so our approach is that we model effects with capabilities. So the following two we treat as equivalent. We say, okay, if we have here t throws e, a function, then clearly that's an effect. The function returns type t, and it might throw exception e. What we model that as instead is we say the function takes a capability, let's call it can throw e, and returns a t. So it's a function that we say it returns a t, nothing else, but to do that it needs the capability to also throw an exception. From a point of view of information, it comes down to the same thing. I mean, in both cases you know that an exception e might be thrown.
Think of that as an argument to f.
It is an argument to f, yeah.
And a value argument.
Exactly, yeah. The using here means it's an implicit argument. The compiler will synthesize it when it sees that the function needs that thing and that capability is available in the environment of the call. So, but otherwise it's just a function parameter, yeah. The thing is actually closer than it just philosophically. So there's a way to get from one to the other in 4 steps in Scala. So if you write t throws e, what that actually is, it's an infix type, so it throws te. So it's a type that has two components, the type that gets the t and the e, the exception. So that alias throws is actually an alias for what we call a context function type. So these are types that, function types that get applied automatically to the result. So it's can throw e to t automatically applied. So the parameter is synthesized at the point where the function is used. So that's what f then is, and this context function type translates into exactly the same thing. It translates into a function that takes this thing as a parameter and returns that thing as a type. So why is that important? Well, it's important because it means that I can actually synthesize and type abstract these implicit capability passing. I don't need to repeat that at every function definition. There's a way to define it once and maybe name that as a type and then use the type everywhere. So these things have been explained in a popular paper 5 years ago, Simplicity, Foundations of and Applications of Implicit Function Types, 6 years ago already. Okay, so why should I bother? Why does that matter to go from functions, from effects to capabilities? Well, it matters for effect polymorphism, and the standard example of effect polymorphism is the map function here. So map, we would write it like this in Scala, so it's defined on lists, it takes a function from A to B, returns a list of B. So if I would have a hypothetical extension of Scala with traditional effects, then somehow I would have to add an effect parameter. So I would say, well, map now takes an effect, E, and it takes a function that returns a B and has this effect, and then the effect of map is also the same effect, E. which might look okay, but really isn't, because map is just the simplest example of something that is absolutely pervasive. We have everywhere calls to higher order functions or virtual method dispatches. So it would mean that essentially everything we do gets these additional parameters, which then accumulate. So you would just get a sea of these effect parameters, and nobody wants to do that. So if you go to capabilities, then interestingly enough, this thing has exactly the same signature it had before. So it's, we say map takes a function from A to B and returns a list of B. So how can that be? I mean, there's something, yes, there's something. So it can be because for us now, the type A double arrow B is a type of impure functions that can capture any capability as a free variable. So function, that's a closure. It closes over the environment. The environment can contain capabilities. That's the idea. I'm going to show some more examples. So we now introduce a new arrow, the single arrow, for pure functions. So A arrow B says that's a function. It doesn't contain any capabilities, but the double arrow is a function that retains capabilities. So serendipitously, Scala always had this, the double arrow as a type of function, so that was a big point of deviation from, let's say, Haskell. But you could say, well, we have just reserved this thing for the pure functions, and it's still available. Okay, so let's see how these things work, and I just pick exceptions. It's not the best domain for effects, I think, but it's one everybody knows. So here we have an application of map. So let's set up the scene. So we have an exception too large. We have a function that throws this too large exception. Just as well, if my number gets too large, I throw the exception. And then we have a list of integers. I map the function over the list, and I do the sum. And that function might throw too large. If it throws too large, I catch it here, and I return another value, right? So the too large thing is, as we've seen, a capability. So if we translate the thing to capabilities, that's what we get. So the function now takes a capability, can throw too large, and it returns an int. Otherwise, nothing has changed. And I have to generate that capability, and that's done here. So the compiler will actually pass this capability to the function. And that's a mechanism that's inherent in the try, because the try catches the capability, catches the exception. There's a capability available that the compiler can pass at this local point. So what you see here is that the function that gets passed to map, it's this function here, right? And that function has a free variable, which is this can throw capability. So it retains this thing in its free variable, and that's why map doesn't have to know about it. Map applies to function. Whatever the function can do, map can do. So it's a different point of view to regard these things. So for us, then map is actually a pure function, because we say map itself doesn't have any effects. The code of map is pure. But of course, if you pass it something impure, that will be impure. So it's a different take from, let's say, the monadic systems. Okay, you say, this is great. I don't need to change my signature. I get effect polymorphism. Where's the catch? Well, there is a catch, and that is that this capability here that I have passed has limited lifetime. So it's only available as long as the try is executing. When the try exits, then there's nobody that can handle this exception anymore. Okay, so here's a way to trick the system into doing something bad. Now, instead of just writing xs.mapf, I write xs.iterator.mapf. So an iterator is essentially a delayed computation. So nothing happens here. And then outside the try, I write iterator.next. So that's the point when the function f will be applied, when I force the next value of the iterator. And of course, at that point, there will be no longer a handler for this exception, and what I get is an unhandled exception. So that's the catch. So if I do these things with capabilities, I need to control I need to know about the lifetime of capabilities, and I need to reflect that in the type system.
It's kind of like laziness.
It's kind of, so iterator and lazy would be the same. So I could also return a closure here. That's, yes.
The the implicit arguments that you have for capabilities, are they always the last arguments, or do you have sometimes need to eta expand to the communication?
That's a good point. So let's see. So here we have an eta expansion, right? We have f, and now we eta expand. And what we do with implicit arguments, which is very important that it happens that way, is we pass all implicit arguments into the eta expansion. So implicit arguments get passed at the point where essentially I form the closure, not later on. Yeah. If you want to pass them later on, you have to make them explicit. Yes?
So to kind of interact with error functions. I mean, imagine I want to call this with one function f that can throw too large and another function f that throws a different exception. So how would that?
That is handled by the map polymorphism. Map would gladly take any closure that throws any exception and just apply it. The type system, it's not reflected in that thing. So that's the beauty of it, that map works that way. Yeah. Yeah.
If you pass this function, this sort of pure function, this function f to map, which is pure.
Yeah.
Map, let's say it wasn't map, but a function that called f many times.
Yes. Yeah.
Then the order in which it called it, the compiler might move that around, but
Yeah.
depending on the effects, that might change the semantics radically.
Why would the compiler move it around?
Oh, just because it's optimizing the code for map.
Ah,
for
right.
wombat.
Yeah,
Let's
yeah.
call it wombat, right?
Yeah.
And it just optimizes the code for wombat.
Yeah.
Previously it called f of 3 and then f of 4, now it calls f of 4, then
Yeah,
f of 3.
yeah.
That would completely change the semantics if it captured an I/O capability.
True. Yeah.
So wombat is not really a pure function, or it's not being given a pure function. How do you control?
Right.
How do you control what optimizations the compiler can do in this allegedly pure?
Okay. So we're not quite there yet. So what we are here is we have the capability system. We can track them, and we can gradually have more and more effects that we capture with capabilities. If you would say we capture all effects that the compiler cares about, then the compiler could just look and say, well, what capabilities get captured? If it's pure, then we're good, and if not, then I can't do these optimizations.
But this is when you're compiling map or
Right.
the wombat
Yeah,
function.
yeah.
And you don't know the callers. They're in different libraries, in 10 years' time. So
Okay.
you don't know the effects that are going to come with the closures that you're being passed.
Right. So you have to specialize then for one or the other. We are looking at that for async. That's a typical one where you say map could be called with a closure that suspends or with a closure that doesn't suspend, and that means map itself can be a suspension point or not. And the idea is that we would specialize the code based on the capabilities that we see in the type system passed to the closure, because at the application point you know whether your closure has possibly an async capability or not. That's the idea.
So functions are no longer truly polymorphic. They have to be specialized for their call signs.
Yeah, they're truly polymorphic in the source, but not for the
Yes.
compiler. The poor compiler, it's not so easy for the compiler.
This is an implementation meeting.
Exactly. Exactly. Okay, so what we want to do is we want to track in a type which capabilities can be captured by its instances. So I have another example here, which doesn't use any compiler intrinsics. So it's a simple try with resources pattern. I have a function using log file. It takes a file output stream, and the way it works is I create a new one. I run the operation on the file that I have created. I close the file, and I return the result of the operation. And that also suffers from the same problem. The operation here might return a closure that accesses the file when the closure is further applied later on. But at that point, the file would already be closed, and essentially that would be an error that would happen. So to rule out these problematic cases, all we have to do is this little hat behind the file output stream. So what that declares is that the operation takes a file output stream which is a capability which we want to track. So the hat says this is essentially an arbitrary capability that needs to be tracked. And that would rule out a use like this, where I say, well, the operation takes an iterator, so it's delayed, and I write, so I would get something like this. So I would say local reference f leaks into the outer capture set of the type parameter t of method using log file. It could probably be improved, so we should work on the error messages, but you get the gist what it does. So the type parameter using log file, it says, well, essentially what happens is that this capability that we passed inside somehow gets returned as a part of type T. So it gets instantiated here, and the system doesn't like that. But on the other hand, if we just wrote map instead of iterator of map, then the compiler would be happy with that. So the compiler knows about one versus the other, about safe versus unsafe usages here. Okay, so how do we do that from a type system point of view? So we have these capturing types, which is a type and a capture set of capabilities. So you ask, what is a capability? Well, a capability is just a parameter or local variable. So that in that sense, it's object capabilities. But if it was any parameter or local variable, the system would be far too verbose, because the free variables of a lambda are something that is very implementation dependent and can change from one point to the next. So we don't want to put these things in the types. The types would get too large and they would change too often. So what we say, a capability is defined by having as its type a capturing type. It's a meta-circular thing. You're a capability if your type needs another capability to exist. So that means that there must be some capability that is essentially from which all others are derived, and indeed there is. It's called cap. So every capability gets its capability-ness or authority from some other more sweeping capability, which it captures, and there's a root capability from which ultimately all others are derived. And I believe that's sort of the type systematic account of the object capability model. And object capability model, as far as I know, it didn't really have a type system so far. I would claim that's essentially a natural type system for that. Okay, so let's make this a bit more concrete. So here we have a mini language, simply typed lambda calculus. The only difference is, since we're talking about capabilities, which are objects, which we want to have in types, this calculus needs to be dependent. So we need to be able to talk about terms in types, but it needs to be only mildly dependent in the form Scala already is. So we just need variable dependencies or path dependencies. We don't need full terms in these types. We just need the references. Okay, so our language then is, so there are lambdas, applications, there are lets, because the other thing I should say, the whole thing is in monadic normal form. So what we want to do is that in an application it's variable to variable. So I assume there's this expansion to monadic normal form. The types are top or the dependent function type, so functions now can depend on their parameters. So these things are the pure types or the shape types. To go to the full types, I need a shape type or a shape type and a capture set. So the full type has a shape type and a capture set, and a capture set is just a set of references. So function type is variable dependent. Terms are in ANF, or rather monadic normal form, because the lets can be nested. And I have the abbreviation that a shape type and an empty capture set, I just write that as the shape type itself.
Martin, were arrows and, I don't know, lists or something in this?
Which one?
Arrows.
Oh, that's the one. Dependent function type. Yeah, that's my arrow.
And what about list of T? Or?
Yeah, that thing is just yeah. So we also have type constructors and things like that. But in that mini formalization, we have just the functions. Okay. Everything is church encoded. So we can show that the Böhm church encoding of lists is actually typable in this system. So polymorphically typable. Okay. So we have a subtyping discipline over this, and subtyping is influenced by a subcapturing relation over capture sets. So there's a relation between capture sets, and this subtyping rule says that if two shape types are in the subtyping relation and the capture sets are in the subcapturing relation, then the full types are in the subtyping relation. So, and here smaller capture sets would give us subtypes. So essentially the type that can do anything is a supertype of the type that can do nothing, that is pure. And pure types with empty capture sets are subtypes of capturing types that capture anything. So the subcapturing thing is essentially subset plus one additional rule, which is very important. It's this one here. This one says if X is declared in the environment to be a shape type and a capture set, then the singleton set X is subcaptures that capture set. So this gives us specialization. So I have this variable X, which essentially has its underlying capture set. It gives it the authority is C, and then we say X is better than C. So, for instance, you could say C is a file system, and X is a logger that needs a file system, so it captures the file system in its thing. So then we say the logger singleton capability is actually a true sub-capture of the file system. It gives you restricted access, but it, of course, in order to work, it needs the full access. But you as a user, if you just hold on to X, you don't have the full access. Okay. So if we use this rule and we instantiated C to empty set, then it shows that, well, if X is a pure shape type, so if it's pure, then the capture set X is a subset of the empty capture set. So that means we can drop all things that are pure from our capture sets. All references that are pure don't show up in these things because of the instantiation of this rule. Okay, so that means we can greatly prune the set of variables that we track. So if we look then at the simple typing system, that's what it is. So it's simply type lambda calculus plus subtyping. And the new parts are in gray, so they're not that many. So I think probably the most important one is here right up at the var rule, where we say, well, if we have a variable that is this type, then a reference to this variable. So the variable is a capability because it has a capture set. I'm now assuming it's not empty. Then the capability of the reference itself is X. I say, well, the capability has the underlying set, so let's type it with X. If C is empty, then it would be again X, but then we know that the capture set X is a subset of the empty set, so it comes down to the same thing. Okay, so then the next rule is for the lambdas, where we say if we look here at a lambda, then we look at the free variables of the body T here, and we subtract X, and that's the capture set of the closure. Pruned with all variables that are pure because we've already seen that we can drop them. So that gives us the true variables that the closure will hang on to.
T should be a variable.
Sorry?
T was a variable in your
T is the body of the lambda. Yeah, sorry. Yeah.
When we say pruned, this doesn't say anything about pruning.
No, the pruning was on the slide before, that where I said, because, well, okay, so we have subsumption. If a type is a subtype of another type, then it has this other type. And by this rule here, we know that if something is like that, then the set X is a subset of the empty set. So that means we can safely drop it from the capture sets via subsumption.
Okay.
Yeah. Okay. Right. So conversely, the application rule says, well, if my function has a capture set, then that's now discarded. The function gets applied. Nobody hangs on to this anymore. So here the capture set goes away. And finally, we have the standard let rule, dependent let rule. So that means that the variable X here can't appear in T2, which is usual because, well, of course, it's local here. But that would mean, the question is, well, what if it does? What if it does appear in the type? Then you have to work with subsumption to actually lift the type to a capture set that doesn't get mentioned locally. And that we do essentially with the subcapturing rule here. Where is it? Yeah, that one here. But we say, well, let's say X is the forbidden local variable. And we say, well, X is actually a subcapture of C, the set it's declared with. So hopefully C will not contain any local variables, so we can pick C instead. So that's essentially this avoidance step here. Okay, so that was the simply typed system, and it's really not very much to it. What we have further is we have extended that to a generic system, so it's essentially an extension of F sub. and there were some challenges in making it generic. So the full system is in our paper that appeared at Toplas and was presented here, but the observation for how to get generic systems is worth a second look. So to add generics to the system, you have essentially two choices. You can say, well, either X, the type variables, are full types. So full types, the type X can range over types that capture things or don't capture things. Or you say X is just a pure type. Type variables have to be pure. And then you need some other way to essentially get a full type into that to essentially make it work so that X can range over things that also capture things. So what we do here is we have this box. We say boxes are things that encapsulate things that can capture things and make them pure. So that means type variables can be instantiated with boxed capturing types, and it turns out that this choice gives us much smaller capture sets and doesn't lose much in expressiveness. So we picked that for the capture calculus. So if we look at boxing, then boxing really, there's a well-known precedent that for boxing we know with type erasure. So when we have type erasure and we have primitive types and we pass them into a generic context, they need to be boxed. They need to be essentially turned into a generic representation. So that happens when primitive type is passed to a generic type variable. We need to box it, and when the generic type variable is instantiated to a primitive type, we unbox it. So we know that from generics. And in our capability system, that's very similar. So only that boxing doesn't create a box on the heap. It hides all captures, returning a pure type, and unboxing re-instantiates the captures in the environment. And what that leads to is a very nice property which I call capture tunneling. So with boxes, captures get masked on construction. So here we have a type constructor. It's simpler than list. It's just cell. So it takes an element and it's generic. It has a type parameter t and an element of type t. Now we have a capability that essentially captures another capability c. And the question is, if I form cell of A, what happens? So what happens when I expand this? Well, I have to infer the type parameter of cell, so that would be A hat C, but it's not A hat C because I say, well, I go into a generic representation here, so I have to box it. So there's this type, what I wrote box in the syntax here, I just write it in ASCII with box. And the same happens in the actual argument that I pass. That argument was an A, but it gets passed to something which is now essentially a box, so I have to box that also. So here's a term level box where I box the type variable, and here is essentially box. Here means, you can say, generic representation, pure representation. What's important is where there's no capture set. So there's no capture set here on the outside, on cell. And that's very important because it means I can actually put these things into data structures and forget about them where they are. I don't need to track every capture that a data structure refers to. So that's the upside of it. On the other hand, when I access things, so let's say I have a function f and is a lambda, and it takes the b and it returns the element of the b. So what happens there is that the type of the element, which is box AC, has to be unboxed on access. It's this unboxed thing here. And what that leads to is that the function f has this type here. So it has type unit to A capturing C, but the function itself also captures C, because in the function I had to unbox, I had to access the capability, so now it's basically this environment that produces the closure that needed the capability because it needed the capability to access the box with the key. So what we see is essentially in a different system we would expect the capability to see here on construction, where we drop it, but what we do is here on access, it pops out again. So that's this idea of capture tunneling, where we hide things on construction and reveal them on decomposition. Ralph?
So if I think of the capability as a value does that mean that kind of the capability value is passed as another argument to f and then gets kind of reattached with the a when that is returned?
Yeah, you could see it that way, but of course that's not the mechanic. The mechanic, it's in the environment of the closure. So it's just that the accounting is as if this value sort of traveled.
Right, but it's in f, it's not in b. So b kind of loses the capability value, and then need to reprovide it when I access its field.
Right, yeah, you can see it that way. Yeah. Okay, so captures tunnel through from construction to decomposition. So you could say, well, this looks all rather hairy. Fortunately, boxes can be inferred. So what the program actually would look like with full types is like this. So there's no box unbox. It's essentially exactly the same as for primitive types and erasure. We know when we need to box and when we can unbox. So all these things happen under the covers. Of course, all these types can be inferred as well, but I just gave you the full types here without the boxes. So essentially, the rules are all type arguments are boxed. Expressions of capturing types passed to instances of type variables get boxed here, and expressions of boxed instances of type variables gets unboxed on access. So if B has this type, then B.lm would get unboxed. And what this unboxed means, it has no runtime semantics. It's essentially just an accounting thing, as we have seen here previously, that it means if you have an unbox here, then the environment, which is essentially the closure here, gets charged with that capability to say that environment now accesses that capability. So essentially that's where it pops out. That's the only effect, you could say, that boxing and unboxing has.
Could this whole slide be polymorphic in C?
Well,
here presumably your C is some fixed.
Yeah.
Right? But could it be polymorphic in C?
Yeah, sure.
So I just add a C parameter to cell.
Yeah, you could do that, yeah.
Cell square bracket C comma T.
Yeah.
And then everything.
Yeah. Oh, no, it's not a type parameter, it's a term parameter. These things are terms. But I can pass them around, and I have a term-dependent language. I can reason about it.
Cell of T, and then I have a C.
Yeah, exactly. Yeah.
But implicitly using C.
You can. That's just a convenience. You can pass it explicitly or implicitly. There's no difference from the type system point of view. Okay, so that brings me to the capture checker. I see I'm actually quite advanced in time already, so I'm going to speed up a little bit. So the task of the capture checker is to recheck a Scala program in a type system where capabilities are tracked and compute all these capture sets. If a capture set is explicitly typed given, then we say that's what it is. But for all the inferred types, we have to produce the capture set component. And the capture checking is, in a sense, similar to borrow checking in Rust. The two are implemented as additional compiler passes for us and also for the borrow checker. So if we look at the Scala compiler in the large, so there's a front end, there's a middle end with 85 mini phases, but they're all very small and they're fused into about 13 phases, about 15,000 lines of code. And somewhere in this pipeline, there's a capture checker that happens, that does these things. And the capture checking is a separate phase. The reason why is, well, it's currently optional, so you can turn it on or off. So you have an import, a special import language experimental capture checking. If you have that in your source, it will be capture checked, otherwise not. It takes time, so it's about as fast as the typer. So that means it's significant for things. So if you don't need it, you don't want to run it. And also, of course, there's a separation of concerns. They're both complex pieces of code, typer and capture checker. And the inference algorithms are different. For the typer, we use local type inference, whereas for the capture checker, it's a form of global inference that we use here. Okay, so in fact, in the compiler pipeline, the capture checker is split into two phases, which we call setup and check captures. So setup prepares types of all definitions for capture checking, and check captures does the actual checks. So before and after checking these capture checking types, if you write them they're treated as annotated types. So this is an annotation, these are arguments, and the Scala compiler generally it just ignores annotated types. So whatever happens, that's just information that gets ignored. So it means before and after capture checking, nobody knows about these capturing types. It's only during capture checking that they get instantiated. So what the setup phase does is it takes these types, if it finds a type with retains annotation, which is explicitly given, then it converts it to a capturing type, and the capturing type has the underlying type parent, it has a capture set, and it knows whether it's boxed or not. So it has this boxing information. It adds box status to capturing types, also explicitly given if they appear in arguments, so they get a boxed. And for all the inferred types, it decorates them with capture set variables. So let's say you have a type previously, let's say a type argument that was inferred to be list of C. Then what the setup phase would do is it would say, well, yeah, that's actually boxed because it's a type argument, so let's add a box. And then it would say, well, the C here, that's a C capturing something that because the type was inferred and I haven't looked at the capture set so far. So let's add a type variable here. And then the whole thing, the list, let's say it doesn't know that lists are pure, that could also capture something. So let's add a type variable here. So on every level of the type, we add fresh capture set variables. Sorry, not type variables, capture set variables, of course. Okay, so then what we do is we essentially run another type checker, but the type checkers are slightly different. So the first type checker, of course, does a lot of type inference stuff, type inference, implicit search, overloading resolution, adaptation to the expected type, and so on. So that's our main typing function. It takes an untyped tree, an expected type, a context, and it returns a type tree. So that's what the front-end typer does. The capture checker is slightly different. It takes now a type tree, that's the type that was previously typed, an expected type as before, a context, and it just returns a type because capture checking doesn't transform the trees. It's just a check. The trees remain the same. It doesn't have a runtime significance here. Okay, and what it needs to do, it needs to infer these capture sets, and it needs to essentially simulate the box-unbox operations because they influence the capture sets in the environments. Okay, just for a quick thing, these are the kind of trees that we see. There are more trees than Haskell, but not terrible. It's still manageable. It's about 25 trees or something like that. So ident selects this, super, type apply, literal. So you see the sort of the type of shape. It's essentially a simple language that has objects and functions and the basics. And then the other thing which is important for the type checker are the map. So basically what the type checker does is it has subtype checks, of course, and it has a bunch of maps that it applies to types. And these maps are basically all homomorphisms that sort of get overridden selectively at some points. And they're all type maps with this definition. So there's a type map, it's a trait, has an apply method, goes from type to types, and there's essentially a pre-configured thing where for every case there's the standard case where we just go homomorphically into the arguments, and you can override that if you want. So some important type maps are substitutions. We need to deal with those. As seen from, which is specific for objects, we need to compute the types of a class member as seen from a prefix. And then the last one is avoidance, which I have shown you already with the let, that we need to sometimes compute types that don't refer to certain variables. We need to find the least super type of these things. Okay, and furthermore, the application points, yeah, I'm going to quickly go. Okay, let's see what we can do. Yeah, so I have to skip that. So essentially, okay, let me just go to the conclusion. Yeah, that's all right. Okay, so summaries. I'm sorry I couldn't get to this part. Ask me afterwards. I can maybe fill in some of the things. So what the capture set that does is it decorates inferred types with capture set variables. It rechecks the program with the usual typing rules, which generate subcapturing constraints on the capture sets. It solves the constraints incrementally using propagation. So for any set, it knows which references are known to be in the set at that point and what the supersets are. And the most tricky aspect is to handle these type maps, because type maps are essentially unidirectional, and we have to know that what happens. So let me just give you to give you a taste. So the hard part is, so we know B is f of A, and f is a type map, and then we also know that B has a new element B. So the question is, what does that mean for the element A? So we get a subtyping constraint, and we have to find an assignment of elements to all these capture sets that makes that true. So we have to find some things in A so that this that this relation can hold. So if f of B is B, that has a simple solution, it's just B, but if it doesn't, then there's a problem. So what we do in this case is we say, well, we don't know what we can put into the A to make this true, so let's make the C bigger. Let's look at the underlying type of the B and try again. And in the end, that will terminate, because at the end, everybody ends up at the universal capability, and all maps map to that. But it's not complete. But in practice, it seems to work fine. Okay, so that was the type maps, and we have to infer the box-unbox operations. So far, we have checked some parts of the Dotty compiler itself with the goal of arena allocation. We have capture-checked most of the standard library, including the collections, frameworks, and futures. And we are working on a new stack of direct style continuation-based concurrency and I/O, which is capture-checked on top of that. So in practice, the annotation overhead is very reasonable. That's the goal we set out to. So to show you how reasonable, I have here the lists in the collection library with a selection of typical operations. And the only thing that I have had to add is these two little hats here, which say for flatmap and concat, this iterable once thing here, that it could actually have an effect. I can append something to a list that as I traverse it has an effect, and that's okay. So I added these two arrows here to say they can have an effect. But if we go to something which is lazy, like iterator, then it's slightly different. So now map returns an iterator, and that iterator retains two capabilities. One is the iterator itself that we have here, because map is lazy, and the other is the impure function f that is also part of the iterator. My point is, this is precisely the information that you want to know. It's not annoying. It's things that if I see an iterator, I really would like to know, yeah, what can it do when I call next? And that's precisely what it tells you. So in that sense, it's really nice. Okay, so to conclude, I think capture-check capabilities have the potential to solve some long-standing problems, including effect polymorphisms, mixing sync and async code, combining manual allocation and GC, fearless concurrency, excluding data races, and they're particularly good in situations where we want to track only a few capabilities. So I wouldn't recommend them for something with Rust, because in Rust it's sort of universal for memories. But if I say most of my programs are purely functional and I have a garbage collector and I don't care about these values, but at some points I do want to essentially do arena allocation or something like that, or I want to care about effects, then these things are good, because these things is essentially you only pay for what you use. So as long as it's purely functional, there's no overhead whatsoever. And otherwise, essentially, the wider you spread your capabilities, the more the annotation overhead increases. So here are some references to find out more. There's a paper. If you Google Scala 3 capture checking, it gives you the details in a doc page. And if you go to this directory repo, you find the source code. Thank you, and I'm already out of time.